So I'll graph this one, but as far as I know, on the first subtest, they don't ask you to graph any trig functions. That's more reserved for the subtest 3 with trig and calc. So you probably do not need this, but I'll go ahead and do it anyway. I'll also send you a link to just kind of graphing these in general if you want it for later, if you ever want to take subtest 3. But a normal cosine graph, once you learn your unit circle, uh, like the cosine. So first I'll just like graph regular old cosine of x. So like the cosine of 0 is 1, the cosine of pi halves is 0, the cosine of pi is -1, the cosine of 3 pi halves is 0, and the cosine of 2 pi is back up to 1 again. And so a normal cosine graph looks like that. And it keeps going on forever, like so. And then, so now we're graphing cosine of 3x, and that 3 does to a trig function the same thing it does to any normal function. So that's a normal transformation where it's going to be a horizontal shrink, where it's going to affect the x's, right, because it's grouped in with the x, that's why it's horizontal. And when it's grouped in like that, it's going to do the opposite of what you might expect. So you're going to divide all the x values by 3. So if I do that, instead of ending at 2 pi, I'm going to end at 2 pi thirds. So I'm going to basically be dividing all these by 3. And it'll kind of shrink so that it ends at 2 pi thirds. And you could just simplify all those values there, pi 6, pi thirds, pi halves, 2 pi thirds. And you can't see it on this, but if you were to graph it to scale, you would see that it would shrink a little bit this way. Notice it didn't do anything to the y's, so the highest is still 1, the lowest is still -1, and that's what you'd be doing for that. The same thing would go for 8, same idea. You've got y equals 3 sine x over 2. And again, as far as I know, you're not going to be graphing these, but it is good if I show you the parent function. You should be able to translate a parent function. That's more the speed of subtest 1. So like a normal sine function, if I told you that y equals sine of x, sine of 0 is 0, sine of pi halves is 1, sine of pi is 0, sine of 3 pi halves is -1, and sine of 2 pi is back to 0. So your normal sine function looks like this, goes on forever, like so. And so if you were given that parent graph, we should be able to tell that the 3 is going to be a vertical stretch. So it's outside, it affects all the y values directly. The y's were this, and now they're 3 times that. So it's a vertical stretch, so all the y values are being multiplied by 3. So instead of going up 1 and down 1, now it's going to go, the max is going to be 3, the min is going to be -3. And then here, just like the last one, this is going to affect the x's because it's grouped in with the x's, and it's going to be a horizontal stretch. All the x values are going to be divided, because it's the opposite of what you expect. It's divided by a half, right? It looks like it's multiplying by a half. It's dividing by a half, which means that it's multiplying by 2. So now the period, instead of being 2 pi, is going to be 4 pi. So on this, we can just kind of multiply everybody by 2 and kind of just graph by changing the numbers around. But I do encourage you to graph it on Desmos, to graph a normal sine, and then to see that the new one will be stretched this way, and this way will be taller and wider. So I'll pause it there, see if it's recording okay. Okay, now this one's fun. So if you were to graph just a normal old log of x, you would have, there's 3 things that I do when I graph a log. I graph the asymptote on the x-axis or the y-axis, and I graph the point 1, 0, because the log of 1 is 0, and then I graph whatever my base is, comma 1. So the base, when they're too lazy to write it, is a 10, and so here I'm going to graph 10, 1, because the log of 10 is 1. What power do I raise 10 to get 10? That's 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. And then, so a normal log looks like that. Now what an absolute value does to a graph is it just makes things positive. So everything that's trying to be negative down here, that's going to flip up and become the positive. And then everything that already was positive will stay positive. So that is your graph of the absolute value of the log of x in orange. And I encourage you to play around with it in Desmos. It's kind of fun. You can graph that, you can graph that, you can see things flipping up. It's pretty fun. Okay, so for this one, they want the range. So if it were just y equals sine of x, your sine goes like that, and the range of it, the y values are going from -1 to 1. So your only question is, does this arctangent limit what you're going to get out of your sine? Well, arctangent, so a little bit of fun. So y equals just regular old tangent looks like this, right? It's got, those are supposed to be asymptotes. Looks like this, and it goes forever like so. So when they do the arctangent, the inverse tangent, since this isn't a one-to-one function, they restrict it to just this one loop, so that this passes both the vertical and horizontal from -pi halves to pi halves. So when they graph the arctan, it just goes from -pi halves to pi halves, and it goes this away. So, because otherwise it would keep going like that and it wouldn't be a function anymore. So, but, after all that, so the stuff you're going to get out of arctan is only going to be between -pi halves and pi halves. So we can only take the sine of stuff between -pi halves and pi halves. So, but this actually doesn't matter, because if I can put in anything to my sine function that's between -pi halves and pi halves, I'm still getting out y values that are between -1 and 1. So my range for this thing actually does end up being the same as for a regular old sine graph. I'm only getting the y values out between -1 and 1. So yeah, that was fun. Okay, so for this one I'm going to think of a normal cosine. I'm going to shift it down 1, and then I'm going to take the absolute value of that. So if my normal cosine is shifted down 1, then it's going to, normally its middle line is at 0. Now it's going to be at -1. Normally has an amplitude of 1, so, and it still does, so it's going to, its new max will be at 0, and its new min will be at -2, and it'll kind of bounce between there and there. So this green, oops, that's sine, my bad. So, oops. So that green is what a normal y equals cosine of x minus 1 looks like. It's the cosine of x shifted down 1. And then what the absolute value will do to it is it'll just make everything positive. So instead of -1, +1, instead of -2, +2, and then it looks something like that. So that's what the absolute value of the graph is going to look like. And so the maximum, it's up here at 2. So the maximum of this thing should be 2. And that, let's see, what do they want? The maximum value obtained by g on the closed interval for x is equal to that. So I see you have the pi circled. It's the maximum does occur when x is pi, but they still want the maximum value, because the way the grammar reads is the max value obtained by g is blah. So the rest of it is just blah. So what they want is the maximum value of the 2. Yes. And then on the closed interval 0 to 2 pi for x, that's just telling you the closed interval 0 to 2 pi is referring to x. Yeah, but I think they want the 2. Okay, that's that. Okay, so these guys you need to know. So for even functions, we know that f of negative x will be the same thing as f of regular x. It'll be the same as the original function. And for odd functions, when you plug in a negative x, you'll actually get the opposite of the original function. So I'll check the normal ones first, because again, the C set 1 and 2 shouldn't cover trig functions that in depth at all. So, but we should be able to look at regular functions and tell if they're odd or even. Now this one, notice it's odd functions, not odd degreed polynomials. There's a difference. So this is an odd degreed polynomial, but it's not necessarily an odd function, which is a little bit annoying. So what we're going to do when we test for odd functions is we're going to plug in a negative x, and negative cubed will overall be negative. And we can see that we're not exactly the same as the original function, so we're definitely not even. And we're not the opposite of the original. If we were the opposite of the original, they would have both been negative. Like it would have been negative x cubed plus 1, which would have been negative x cubed minus 1. So we don't equal that, so this is nothing. This is nothing. You can tell from the graph too, like a x cubed popped up 1 would look like that. It has symmetry over this point, but odd functions have symmetry over the origin. And once you add 1 to it, you lose the symmetry over the origin. So like a normal x cubed, that's odd, but as soon as you hike it up 1 or translate it, it's not going to work anymore. So that is the answer, C. But we should check the other ones just so you can see why they work. So I'll do D, f of x equals x over x squared plus 1. So when I plug in f of negative x, I replace the x's with negative x's. And I can see that I'm not my original, so I'm not even, but I am the opposite of my original, right? If I just slapped on a negative to the original function, yeah, I match, right? Notice you don't do it to top and bottom, otherwise you'd be dividing by a negative 1. It's just negative this, and you can choose to give the negative to the top or the bottom. So that guy is good. That is odd. And then for E, same thing. If we go look at what happens when we plug in a negative x, we're getting the cube root of 2 times negative x, which is the cube root of negative 2x. And for a cube function, you are allowed to go ahead and pull out that negative from the cube root. This is okay. If it were an even power index, you could not do that, but here you can. And so you notice that it is the opposite of the original function. So that's odd. If you don't buy this, you can check it. Like, what if you had the cube root of negative 8? That's negative 2, which does equal negative the cube root of 8, negative 2. So we can pull it through. It's all right. We're not afraid of odds. So you might have been, your question might have been for the trig functions because it seems like you're a little worried about those. But again, I don't think you have to be for the first two subtests. So y equals sine, that is a classic odd function. It is nice and symmetric over the origin. That's odd. If you plug in the sine of negative x, it will be the same as the sine of x. So that's A is definitely odd. And then for B, when you see y equals the sine of 2x, you know that 2, all that's doing is doing a horizontal shift or a horizontal shrink. So it's just getting a little bit shrunk, but it still is going to maintain that symmetry. Nothing's happening. Translations mess it up, but shrinks and stretches are fine. So this guy is still odd, and that's okay. Cool. Okay, so what we want for this one, they want the range. And if it had been like a normal ln of x, normal ln of x looks something like that, goes through that point 1, and it goes all the way up and all the way down. So a range of a normal ln of x is everything, negative infinity to infinity. Our only problem might be what we're getting out of this cosine of x, right? So your cosine of x looks something like this. And the things that you're getting out of cosine of x are only between negative 1 and 1. So this value in here is always going to be between negative 1 and 1. So the ln, I'm only going to be taking the ln of things between negative 1 and 1. So the only y values I'm going to be getting out of here are things that are less than 0, because the highest, right, when I take the ln of 1, I'm getting 0, and if I take the ln of anything between negative 1, I mean, I won't be able to plug in this, I've got some domain issues too, but I'm not going to be able to find the ln of 2, 3, 4 because I'm not going to get that out of cosine, so it's just this guy, and the y values here are the y's that are less than 0. Can we equal 0? Yeah, we can, because when you do the ln of 1, that equals 0, so we're good. So I think on your answer choices, it's A, between negative infinity and 0. That's kind of fun. Cool. Okay, so for this guy, if you had a normal just e to the x, it looks a little something like that. So that's just normal e to the x. So the range of this guy is just that the y's are greater than 0. But now we're like, okay, well, does that restrict anything, that tangent of x? Am I getting all the possible values of x I can get out of that? And yeah, because the tangent of x is, the tangent looks like that. So that's y equals tangent of x, and it goes from negative pi halves to pi halves. So you see that the outputs of the tangent of x are all the way down from negative infinity to infinity. So we're getting every single possible value we can out of that tangent of x. So it's not going to affect the range for this guy at all, because we're not going to be restricted in these values. So my range will just be the normal range of e to the x, just y's that are greater than 0. And that should do it. So y's that are greater than 0. So that's B on yours, from 0 to infinity. That's kind of fun. Okay, so your normal sine ends at 2 pi, and this is pi, and this is pi halves, and this is 3 pi halves. And this guy, when you have that x divided by 3, it looks like the x's are being multiplied by a third, but instead we're going to divide the x values by 1/3. So we're essentially multiplying the x values by 3. So instead of ending at 2 pi, it's going to end at 6 pi. But mainly we're concerned about where they ask for where the maximum is. So normally the maximum is here at pi halves. If we multiply that by 3, we're at 3 pi halves. So that's where the maximum of this graph is. When you shift it down 1, because that's all that's doing, your maximum will still be here at 3 pi halves. So 3 pi halves is an answer. That's C. We rock. Okay, so I'm going to just create f of g of x first. So f of g of x is ln of 9 minus x squared. And so to get the domain of a composition, you first have to consider the domain of the inside, because this g of x had to exist before you plugged it into f. And the domain of the inside was just all real numbers. Okay, no restrictions there. And then you consider your new function, the ln of 9 minus x squared, and like, uh-oh, ln's, we've got some restrictions here. We need to make sure that an inside of a log is greater than 0. So to solve this, if you've got an inequality of something that's nonlinear, you've got to do your sign line and factoring, or however you like to do it, but you can't just throw the 9 over, divide by a negative, and square root both sides. You can do that to find out where it's equal to 0 at -3 and 3, but to figure out whether it's positive or negative, you have to be really careful with the inequality sign. So if I plug in anything bigger than 3 into this, like 100, I'm getting a negative times a positive. I'm negative over here. It'll alternate on down, or you could picture the upside down parabola graph going like that, so that it's negative over here and negative over here. Since it's greater than we want the positive stuff, so the positive stuff is going to happen between -3 and 3. So I'm only allowed to plug in functions between -3 and 3 into this, otherwise I'm taking the ln's of negatives, and that's just terrible. So your domain should be between -3 and 3, and we're not allowed to equal it because we can't take the ln of 0. That's no good. So we're strictly greater than when you set the insides of logs greater than 0. So that's the domain. Okay, so for the range of this thing, again, we're going to first consider just a normal ln of x. So just your normal ln of x has a range from -infinity to +infinity. There's no restrictions. You can get any y value out of it. So your only concern is whether this is going to restrict what we can put in. So 9 minus x squared looks a little something like that. And the only y values that I'm getting out of here, oopsie, my only outputs are less than 9. So I can put in anything, like I'm getting out outputs are y values that are less than 9. So the only thing that I'm going to get in that are y values that are less than 9. So I'm only going to be plugging in into here things that are less than 9. So I'm going to cut off right there. And I'm only going to be able to get y values that are less than the ln of 9, because that's the max that takes, and I can go all the way down. So the range for this guy are going to be y's that are less than the ln of 9. So just part C there, that y's that are less than or equal to the ln of 9. And I can equal it to, because that's okay, because if x were 0, I would just get the ln of 9, and that's the ln of 9. That's fine. And then I can get all of those guys. But since I'll never get like a 10 out of here, I'll never be able to take the ln of 10 because that won't be an output of that guy. Kind of fun. There you go.